the unspoken ambition. It hangs in the center of the laboratory, like a relic from a future civilization. A cascading golden chandelier of twisted wires and polished copper, suspended in a silence so profound it feels heavy. Inside this vessel, the temperature is lowered to near absolute zero, a cold deeper than the void between the stars. To the outside world, this machine, the quantum computer, is the future of finance and cybersecurity. You are told it will revolutionize drug discovery, optimize supply chains, and crack the uncrackable codes of the internet. That is the safe, sanitized story they tell the shareholders. But if you lean in close, past the corporate press releases, and listen to the physicists who actually build these leviathans, you will hear a different ambition. A whisper that suggests something far more dangerous. They aren't trying to build a better calculator. They are not trying to speed up the internet. Their true, unspoken goal is to build a mirror. They are attempting to engineer a machine that doesn't just process data about our reality, but replicates the operating system of reality itself. They are building a pocket universe. Before we descend into this rabbit hole, I need to set the stage. This is not a 5-minute tech update you watch while scrolling on your lunch break. We are about to cross the threshold into one of the most vertigo-inducing frontiers of modern science. We are going to talk about the origin of the Big Bang, the pixelated texture of space-time, and the terrifying possibility that our own reality is nothing more than code running on a machine, just like this one. This story demands your full attention. So, settle in. Close the other tabs. If you are ready to see how humanity is attempting to steal fire from the gods and rewrite the laws of creation, I want you to commit to taking this journey with me until the very end. Because the implications of what we are about to discuss don't just change technology, they change what it means to be alive. To understand why this is happening, we have to travel back to a specific moment in 1981. It was a conference at MIT, a gathering of the brightest minds in physics. It was here that the legendary Richard Feynman stood up and dropped a bombshell that would become the genesis of this entire field. He looked at his colleagues and famously declared, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." Feynman had realized a flaw in how we were doing science. For centuries, we had been trying to understand the violent, chaotic birth of our cosmos, using mathematics and machines that speak binary, 0 and 1. We hit a mathematical wall known as the sign problem, where classical logic collapses under the weight of quantum reality. But the universe is not binary. An electron is not here or there. It is a ghost, existing in a haze of probability, spinning in multiple directions at once until it is observed. Trying to simulate the Big Bang on a classical computer is like trying to play a complex symphony on a slide rule. You might get the tempo right, but you will miss the music entirely. Think of it this way. If you want to predict the weather, you can use a classical supercomputer. It will take data, wind speed, humidity, temperature, and it will crunch the numbers. It is essentially a very powerful calculator, doing math about the wind. But it is not the wind. The numbers on the screen do not blow the papers off your desk. However, if you really want to understand how air flows over a wing, you don't just do the math. You build a wind tunnel. You create a physical environment that obeys the same laws of fluid dynamics as the sky itself. You aren't simulating the air. You are emulating it. This is the heart of the unspoken ambition. Current computers are the calculators. Quantum computers are the wind tunnels. The quantum processors inside those golden chandeliers, like Google's Sycamore chip, are not merely running equations. They are manipulating qubits that exist in superpositions and entanglement. These qubits obey the exact same strange laws as the particles that made up the infant universe. This is what we call the hardware-reality isomorphism. The machine and the cosmos share the same source code. They are building a toy model of creation, testing the limits of existence in a controlled environment. When a physicist runs an experiment on a quantum computer, they are not just modeling physics, they are creating a closed system that is physics. If they program the machine to simulate a wormhole and the data teleports across the chip, they haven't just calculated a wormhole. In a very real mathematical sense, they have forged a microscopic tear in space-time within that lab. They are acting as architects of a new reality. And this leads us to the ultimate question, the one that keeps these scientists awake at night. If we can build a machine that simulates a universe from scratch, how do we know we aren't already living inside one? To truly grasp the magnitude of what these scientists are attempting, you have to understand that for 50 years, physics has been stuck, hitting its head against a wall. We have known the equations that govern the universe since the days of Schrödinger and Heisenberg. We have the recipe for the cosmos, but having the recipe is very different from being able to bake the cake. When physicists tried to feed the conditions of the early universe into the most powerful supercomputers on Earth, the machines didn't just slow down. They choked. They hit a barrier known as the sign problem. This was not merely a failure of engineering or a lack of processing speed. It was a prohibition of nature. In the classical world, the world of standard computers and human intuition, probabilities are always positive numbers. There is a 50% chance a coin lands on heads, or a 0% chance it turns into a bird. But in the quantum world, the math allows for negative probabilities. When you try to simulate the chaotic, superheated first seconds of the Big Bang on a classical chip, these positive and negative values cancel each other out in complex, unpredictable ways. The signal vanishes. The data turns into noise. The computer is trying to track billions of subatomic interactions that are all entangled with one another, and the math collapses under its own weight. This creates a terrifying issue called exponential overhead. If you want to simulate a quantum system, every time you add a single particle, the memory required to track it doubles. It seems manageable at first. One particle is easy, two is trivial, but the curve is merciless. By the time you try to simulate just 300 entangled particles, a microscopic speck of dust, in the grand scheme of creation, you would need a classical computer with more memory bits than there are atoms in the visible universe. Think about that scale. Trying to map the universe on a classical computer is like trying to store the entire Library of Congress in the margins of a single paperback book. The information density of reality is simply too high for our traditional tools to handle. We were trying to paint a masterpiece with a sledgehammer, and for decades, the early universe remained a dark, unreadable era. We could theorize about it, but we could not test it. We were locked out of the library. This brings us to a pivotal moment of reflection. I want you to pause and think about that lock for a moment. We often assume that with enough computing power, humanity can eventually solve anything. But here, nature seems to have a built-in encryption that defies brute force. Do you think there are fundamental limits to what we can know? Or is this just another puzzle waiting for the right key? I am curious to hear your perspective. Tell me your theory in the comments below. The key, as it turned out, would not come from building a bigger hard drive. It came from a change in philosophy. The turning point arrived in 1981 at a now legendary conference at MIT. Richard Feynman, the bongo-playing Nobel laureate and arguably the most intuitive physicist since Einstein, stood before his colleagues and shattered the paradigm. He looked at the failure of classical simulations and realized the problem wasn't the computer's power. It was the computer's language. We were trying to simulate a quantum reality using binary logic, zeros and ones. But the universe doesn't run on binary. It runs on amplitudes, superpositions, and interference patterns. Feynman famously declared, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." It was a prophecy that would take 40 years to fulfill. Feynman was suggesting something radical. Stop fighting the laws of physics and start using them. If the universe is built on quantum mechanics, then the only machine capable of simulating it must also be built on quantum mechanics. We didn't need a faster calculator. We needed a machine that ran on the code of nature itself. This was the birth of the God-machine concept. The goal shifted from computation to emulation. If we could build a device where the components, the qubits, obeyed the same laws as the particles in the early universe, we wouldn't have to calculate the outcome of the Big Bang. We could just set up the initial conditions, press play, and watch it happen right there on the chip. Feynman's ultimatum made one thing clear. To understand the machine of God, we had to stop acting like mathematicians and start acting like creators. We had to build a system where the hardware and the reality it simulated were one and the same. And to do that, we would have to master the most fragile thing in existence. That fragile thing is the qubit. And in November 2022, inside a lab at Google, a team led by physicist Maria Spiropoulou used those qubits to do something that sounded like science fiction. They didn't just calculate how a wormhole works. In a very specific mathematical sense, they built one. Using the Sycamore quantum processor, they entangled 9 logical qubits in a pattern designed to mimic a traversable wormhole. When they fed a pulse of information into one side of the system, it scrambled, disappeared, and then instantly reassembled on the other side. It didn't travel through the wires. It traveled through a shortcut in the geometry of space-time that the computer had generated. This was the holographic ghost. It wasn't a physical tunnel you could walk through, but the information behaved exactly as if it had traversed a gravitational wormhole. To understand why this terrified and thrilled the physics community, you have to understand the holographic principle. And to understand that, I want you to imagine a soda can. You hold this 3D object in your hand. It has volume, depth, and contents. Now, imagine you crush that can flat, smashing it into a perfectly two-dimensional metal puck. The can is gone, but the information, the label, the barcode, the ingredients list is still there, just scrambled across the flat surface. If you knew the laws of physics perfectly, you could look at that flat, crushed circle and mathematically reconstruct the 3D can. The 2D surface holds the entire reality of the 3D object. This is the essence of the ADS-CFT correspondence, the Rosetta Stone of modern physics. It suggests that a universe with gravity, like the one we live in, is mathematically identical to a flat quantum field without gravity. They are the same thing, just viewed from different angles. This brings us to a question I want you to really sit with for a moment. If a two-dimensional chip can project a three-dimensional wormhole, and if the math says our universe works the same way, where does that leave us? Are we the 3D can? Or are we just the data smeared on a 2D surface somewhere else? I'd love to read your theories in the comments. Are we the solid object, or just the holographic projection? Back in the Google lab, this wasn't just philosophy, it was engineering. The Sycamore chip was the flat, crushed soda can. The wormhole was the 3D ghost that emerged from it. This experiment provided the first experimental hint of something radical, that space-time itself is not fundamental. For centuries, We thought space was the stage, and gravity was a force acting on the actors. But inside the quantum computer, gravity wasn't programmed in. It emerged. When the qubits became entangled in just the right way, the geometry of space-time appeared as a side effect. It suggests that gravity, the force that holds your feet to the ground and keeps the planets in orbit, might just be a byproduct of quantum entanglement. It's a holographic projection arising from the deep connections between particles. The scientists didn't write code for gravity. They wrote code for entanglement, and gravity popped out of the equations like a ghost in the machine. This is the aha moment that changes everything. If we can build a machine that generates its own gravity and its own space-time geometry simply by entangling information, we aren't just simulating a picture of the universe. We are building a low-resolution version of reality itself. But if space-time is just a projection coming from a lower-dimensional grid of qubits, it implies that our reality has a limit, a resolution. If you zoom in far enough, past the atoms, past the protons, does the smooth fabric of the universe eventually break down into a grid of pixels? Because if it does, we have a way to find them. When you look out a window or watch water pour into a glass, reality feels seamless. It flows. There are no gaps, no jagged edges. For centuries, this is how we assumed the universe worked, a smooth, infinite canvas where you could zoom in forever and never hit a bottom. But the architects of quantum computing see something different. They are suggesting that the smoothness of space-time is just a trick of perspective, much like how a movie looks like continuous motion, despite being 24 still images flashing before your eyes every second. We are simply too big to see the seams. To simulate the universe, you cannot assume it is infinite. You have to break it down. Physicists use a framework called lattice gauge theory. It treats space-time as a rigid grid of discrete points, like a video game wireframe. Imagine a 3D chessboard. Particles, quarks, electrons, photons, don't glide through the empty space between the squares. They hop from one intersection point to the next. In this model, the universe has a resolution. It has a pixel size. We call this pixel the Planck length. It is unimaginably small, but it is there. And if it is there, it means reality is not analog. It is digital. It is built from blocks. Think about a high-definition photograph. From a distance, the curve of a human face looks perfectly smooth. A sunset looks like a blend of color. But you know what happens if you zoom in? You zoom in once, and it still looks clear. You zoom in again, and the edges start to blur. You zoom in a third time, and suddenly, the illusion shatters. You don't see a face anymore. You see a grid of red, green, and blue squares. It looks less like a photograph and more like a Minecraft world. The smoothness was just a result of your inability to see the grid. If you look closely enough at our world, you might find the exact same thing. Pause for a moment and sit with that image. Look at the wall across from you, or the skin on your arm. If I told you that if you zoomed in far enough, past the cells, past the molecules, past the atoms, you would eventually hit a hard limit where the curve of your reality turns into a jagged, blocky staircase. How would that make you feel? Would it make the world feel fake? Or would it make you feel closer to the source of it all? Let me know in the comments. Does a pixelated universe terrify you, or does it make perfect sense? This is why classical supercomputers have failed to give us the full picture. When they try to simulate this lattice, specifically the early universe, they hit a mathematical wall known as the sign problem. The quantum calculations cancel each other out, and the simulation crashes. They simply cannot handle the resolution. But a quantum computer doesn't have to simulate the grid. In a way, it is the grid. By mapping the quantum fields of the universe onto the qubits of the chip, we are building a low-resolution model of existence itself. We are creating a pocket universe obeying the same rules as the one outside. This leads to the most unsettling realization. If space-time is a lattice, and if the universe has a maximum resolution, our reality is indistinguishable from a simulation. A true organic universe should have no bottom. You should be able to divide space infinitely, but a simulation always has a limit. It always has a pixel size determined by the machine's processing power. If these quantum computers succeed in simulating the Big Bang using lattice gauge theory, they won't just be revealing how the universe began. They might be revealing that the fabric of space is code. And if we can build a machine that runs that code, we have to ask, who built the machine that is running us? The moment you ask, who built the machine running us, you step off the solid ground of physics and into the free fall of the simulation hypothesis. It is a terrifying thought, but our work with quantum computers is forcing us to confront it. When we stare into the heart of a dilution refrigerator, that gleaming golden chandelier of twisted wires and supercooled plates, we are not just looking at a piece of hardware. We are looking into a recursive mirror. We are attempting to build a reality within a reality, constructing a vessel that can hold the infinite complexity of space-time within a few subatomic particles. Consider what we are actually asking these machines to do. Physicists are not just simulating peaceful, static galaxies to admire their beauty. They are running doomsday scenarios. They are actively simulating false vacuum decay. In our current understanding of cosmology, it is possible that our universe is sitting in a false energy state, like a ball resting precariously on a ledge rather than the bottom of a valley. If that ball were to be nudged, if the energy field were to tunnel to a lower state, a bubble of true vacuum would nucleate and expand at the speed of light, incinerating matter and rewriting the laws of physics instantly. We are terrified that this might happen to us. So, what is our solution? We are trying to make it happen inside the computer first. We are using qubits to model these catastrophic phase transitions, watching to see how a universe destabilizes and consumes itself, hoping the glass of the simulation holds. I want you to pause and really sit with that for a moment. Look around the room you are in right now. Touch the surface of your desk or the arm of your chair. It feels solid, doesn't it? It feels undeniable. But if we can replicate that solidity, if we can write code that feels this real to the entities inside it, does your confidence in your own reality start to shake? I want to know where you stand on this. Do you believe you are in base reality, the original uncreated universe, or are we just another layer in the code? Go down to the comments right now and type base reality or simulation. Let's see which side of the mirror we are collectively standing on. By simulating these phase transitions, we are essentially building a model house and setting it on fire to see if our own house is flammable. But there is a deeper, more existential risk in this experiment. It is the risk of success. The moment we successfully simulate a self-sustaining pocket universe, even a tiny one, we cross a philosophical event horizon. We prove that a universe can be created by intelligence. We prove that reality is computable. This realization dismantles the ego of our species. Think of it like a set of Russian nesting dolls. For centuries, we assumed we were the biggest doll, the outermost shell, the only reality that mattered. We believed we were the base reality. But if we can craft a smaller doll to fit inside us, a digital universe running on a quantum chip, then the logic forces us to look upward. If the doll inside us exists, why should we assume we are the outer shell? Once you accept that universes can be simulated, the math dictates that there will be billions of simulations for every one true base reality. Statistically, it becomes infinitely more likely that we are just one of the middle dolls, encased within a larger machine, which is itself sitting on a desk in a universe we cannot comprehend. This is the vertigo of the recursive mirror. We are racing to build a machine that plays God, desperate to understand the Big Bang. But the closer we get to that goal, the more we reveal our own potential artificiality. We are trying to read the mind of God through our circuits, only to find that the code we are writing looks suspiciously like the code that wrote us. We are pulling back the curtain on existence, terrified that we might find a screen. We are looking for the origin of the universe, but we might just be finding the edge of our own programming. This brings us to the ultimate vertigo. When we stare into the cryostats, watching those golden chandeliers cool down to absolute zero, we are not just building a tool. We are stepping into the role of the architect. The architect learns that creation is strictly a data problem. Decades ago, Richard Feynman slammed his hand on a podium and declared that nature isn't classical. He understood that to copy the cosmos, you cannot use the clumsy approximations of standard math. You must speak the native language of reality, quantum. Today, we are validating a theory physicist John Archibald Wheeler called it from bit. The concept is radical yet simple. At its foundation, the universe is not made of particles or matter. It is made of information. Every electron, every galaxy, is ultimately just the answer to a yes or no question. Reality, at its core, is binary. Think about the implications. We used to believe that to build a universe, you needed infinite energy. But the quantum architect realizes you only need enough qubits to hold the state. The Google Sycamore chip didn't need a galaxy's worth of matter to create a wormhole. It needed 9 logical qubits. It suggests that the grandeur of the cosmos is a projection of something flatter, simpler, and much more like a computer chip. To make these simulations work, scientists use lattice gauge theory. They chop the smooth fabric of space-time into a discrete grid of points, pixelating the universe to make it computable. It looks suspiciously like the voxels in a video game. And the shock is that the physics holds up. The simulation behaves exactly like our reality. This forces the architect's dilemma. If we can recreate the birth of a universe by treating space as a grid of information, we have to ask why our own universe has a hard resolution limit. We call it the Planck length, 10 to the power of negative 35 meters. It is the pixel size of our reality. We are discovering that the math used to build the simulation is identical to the math that governs the simulator. We are trying to read the mind of God, hoping for a divine inscription, but instead, we are finding error correction codes. We are looking into the cosmic mirror of a quantum processor, expecting to see a machine, and instead, we see our own reflection staring back. The boundary between the creator and the creation is not just blurring, it is dissolving. We are not just simulating a universe, we are decoding the structure of the one we inhabit. This leaves us with a heavy, haunting realization. We built these machines to find answers, but they have only given us a mirror. If the universe is code, and we are now writing that code, are we the players? Or are we just part of the program that has finally become self-aware? I want you to sit with that for a moment. If our reality is pixelated, just like the simulations we are building, does that make you feel insignificant? Or does it make you feel like you are finally seeing the truth? Tell me in the comments below. I read every single theory you post. And if you want to keep peeling back the layers of this cosmic code with us, make sure you subscribe. We are only just beginning to decode the infinite.